Today we're going to talk about oxidation-reduction reactions, or we call them redox for short. Specifically, we're going to talk about how to combine half reactions to balance a reaction. First, I want to point your attention to table 19.1. This is from the textbook, and it's on page 591. It's very helpful in listing some of the common rules for assigning oxidation numbers. If there's an element that's by itself, it's going to be 0 unless it has a charge, like it's an ion. Also, I want to point out that things like chlorine gas or oxygen gas, any of these covalent compounds that are going to share electrons with itself, these are the diatomics or the Brinkelhoff elements. These would all have an oxidation number of 0 because there's not going to be one of them that will give and one that will take. They're just going to share them. You can go down and read the others. I just want to point out number 8, the sum of the oxidation numbers in all of the compounds or atoms is going to equal 0, except for when there's a charge at the top. For example, if you had this compound, notice that there's a -1 charge, and that means that all of the oxidation numbers for all of the elements in this compound would add up not to 0, but to -1. So I just want to point that out because that can cause some confusion. So take some time to review that chart. We're going to do a couple of examples here, starting with this one. This one has 10, and then notice this second one is an ion, so there's a -1 charge, so it's not going to add up to 0, it'll add up to -1, and then you get 10 in iodine. So let's start looking at our oxidation numbers. 10 on this side has a +2 charge, and that's just given to you, so there wasn't a whole lot of work there in trying to determine that. On this side, 10 has a +4. Okay, so 10 went from a +2 to a +4, so 10 is oxidized. Okay, oxidation is loss of electrons, and remember our oil rig here, oxidation is loss of electrons, reduction is gain of electrons. So 10 lost some electrons, which is why it became more positive. Protons don't change. It actually lost 2 electrons in the process. If you'll notice, on this side you have a total of a +2 charge. On this side you have a +4 and 2 negatives, which would also equal a +2. So the numbers need to match on each side. Okay, let's look at iodine over here. This whole compound has a -1 charge. Why? Because it has a negative there. So that means when you start adding up all the oxidation numbers here, it has to equal this number. Each oxygen, I'm going to start with oxygen because he is more stable as far as, he's more predictable. Typically an oxygen is a -2 unless he's in a peroxide. You can look back at that table. So each oxygen in this compound is going to have a -2 charge. He'll take 2 electrons. There are 3 oxygens all together, so if each of them have a -2, there's a total of -6. So 6 electrons are going to be taken all together by all the oxygens. Well, in order to find out what iodine is, if the total charge is -1 and oxygen takes 6, you can think of it as an algebra equation. So iodine has to be some number so that the total is -1. And so then X is equal to a +5. So iodine here is a +5. And since he's uncombined on this side, then he's a 0. Don't worry about where the oxygen goes. Again, this is not a complete reaction. It's just to show or demonstrate how oxidation-reduction reactions are made. Okay, so iodine is a +5 over here. Okay, and he's a 0 over here. So he is reduced. Okay, and reduction is gain of electrons. So iodine gained electrons. Well, if he went from 5 down to 0, he must have gained 5 electrons. And you put it on this side. Okay, so you have a +5 and a -5, that equals 0, and then you have a 0 on this side. Now what I want to do at this point is balance the reaction by balancing the electrons. So basically what that's saying is that you can't gain 2 electrons in one element and lose 5, gain 5 electrons in one and lose 2 in another. That doesn't balance out. You have to gain and lose the same number of electrons in the reaction. So the number of electrons need to be the same. So when you look at these two numbers, you want them to be the same number. Well, what I do is I look at my least common multiple of 2 and 5, and that would be a 10. So I want to have 10 electrons lost and 10 electrons gained. If I do that, then that means this whole half reaction has to be multiplied by 5 so that I can get 10 electrons. This whole half reaction has to be multiplied by 2 so that I can get 10 electrons down here. So I'm going to rewrite this as it's after it's been multiplied, and then we'll add them together and let's see what happens. So we have 5 10 twos making 10 electrons and 5 10 fours. Okay, clean that up. Okay, so basically what you're doing is we're trying to balance out the reactions. Okay, we'll multiply this. We have 2 iodine plus 5s plus 10 electrons because I'm distributing. And then we get 2 iodines. All right, now we want to add all this up and get the total reaction with the electrons. Okay, if you'll notice, my electrons now cancel. Okay, I have the same number being taken as being given, so I can just simplify by saying I have 5 10 twos plus 2 I5s making 5 10 fours and 2 I's. And this is your balanced reaction. Okay, let's try another. Okay, our sulfur over here is a -2. We know that because it's given, so that makes it easy. Our sulfur on this side is a 0. He's uncombined. There's nothing he hasn't gained any electrons or lost any electrons, so there's nothing going on there. Now, if I go from a -2, if you think about a number line, here's 0, here's -1, here's -2. Okay, if I'm going from a -2 up to 0, then I'm actually becoming more positive, and I'm losing electrons. And so if I'm losing electrons, I'm actually being oxidized. So oxidation is loss of electrons. So I'm going to have 2 electrons that I've lost plus sulfur. Okay, now let's look at this nitrate ion. Again, don't forget about that negative. Okay, so you have NO3 with a negative. So that means the total charge of the whole compound has to equal -1, not a 0. Each oxygen is going to have a -2 charge. You have 3 of them, so a total of -6 electrons will be taken by oxygens. So that means that our nitrogen must be losing 5 electrons because there's 1 left over. So we're going to go from a nitrogen plus 5 on this side, and probably he's going to gain electrons. And the reason I know that is because in order for sulfur to lose electrons, that means someone else must be gaining them. Okay, now let's look at NO. Okay, there's no charge here. That means the total is going to equal 0. So if oxygen is a -2, there's only 1 oxygen, so he'll be a -2. So that means that nitrogen must be a +2 in this compound. Okay, so I go from a nitrogen to a nitrogen +2. Now, to go from 5 down to 2, okay, reduction is gain of electrons. I'm going to need 3 electrons. Now, this is the second part here. I want to balance the reaction. I've got my half reactions all set up. I'm good to go. But now I need for 2 and 3 to be equal. So the least common multiple of 2 and 3 is 6. Okay, so I'm going to multiply this times 3 and this times 2. You don't always multiply them by the other number. It just so happens that's how it worked out here. So now I have 3 sulfurs, making 6 electrons and 3 sulfur zeros, 2 nitrogen 5s plus 6 electrons, making 2 nitrogen 2s. Okay, to find my total half reaction, I've got 6 electrons on the right, 6 on the left, so I can finish with this. 3 S2s plus 2 N5s. And there is my answer. Okay, we'll do one more. Okay, let's look at our last example. This example is a little bit tricky when you first look at it. When you start going through all the balancing, let's look at ammonia. And hydrogen's a +1, so there's a total of 3 lost electrons. We're going to equal to 0 because there's no charge on any of these, so all of these will balance to 0. So nitrogen in this particular compound is a -3. Oops, that's a -3. Okay, then we'll look at our next one and see that NO2 is also equal to 2. Well, if each oxygen is a -2, you've got 2 oxygens, so that's a total of -4. That would mean nitrogen in this compound is a +4. Well, that's kind of interesting because up here nitrogen was a -3 and here nitrogen was a +4. Hydrogen will not change. This hydrogen is still going to be a +2 and oxygen won't change, but there's 2 different nitrogens that you've mixed into this reaction, and they're going to do 2 different things. This nitrogen is going to be 0. Now, remember whenever I talked to you about diatomic molecules, they're going to share their electrons, and so it's always going to, there's not going to be any giving or taking. So you have a nitrogen over here that's a -3, and a nitrogen here that's a +4. So in this particular equation, you have a nitrogen -3 going to a 0, and you have a nitrogen +4 going to 0. Now here you are oxidized. Oxidation is loss of electrons, so I'm losing 3 electrons. And down here you're reduced. You went from 4 down to 0, so you're gaining 4 electrons. Now we just need to balance the reaction. We have 3 electrons here and 4 there. They don't balance, so our least common multiple is 12. It just so happens that's the other number. So we can rewrite this. So we can rewrite this and then we can rewrite this one. Okay. These cancel when you're adding them together because this is the whole reaction. So you have 4 of these. Okay. And then on this side you can combine them so that you would have a total of 7.